Yeah, good morning, everyone. My name is Jonathan Sugarman, and I'm working with Dr. Wayne Strasser with Liberty University on my undergraduate research, the validation of a shock wave in a converging diverging nozzle. Um, oop. So first, we'll just go briefly over kind of how that works and what I'm trying to simulate. So you all know jets and rockets travel extremely fast, supersonic speeds, faster than the speed of sound. And this is often done using a converging diverging nozzle, CDN, or a Laval nozzle, pictured here, with your inlet on your left, your throat in your middle with a minimized area, and then your outlet on your right. And essentially what's happening is accelerating hot gas through the nozzle to create thrust and move that vehicle. And basically pressure differential drives this flow. So if your pressure at your outlet and pressure inlet are the same, nothing's going to happen. But if your pressure at the outlet is less, you get your flow through. So an interesting phenomenon happens if the pressure outlet relation to the pressure inlet is sufficiently low. Um, you'll have your subsonic flow coming in from the inlet, and then it will get sonic at the beginning or at the throat, and then a shock wave will occur in the diverging region, and that location will depend on your geometry and your pressure ratio. But yeah, essentially the pressure waves bunch together and form a shock wave, and that means that you've got supersonic flow before you shock and sonic flow or subsonic afterwards. So the rationale and the goal of this research is that ANSYS Fluent should be able to simulate this behavior. It's a very robust CFD solver. I'm sure you all are familiar with it. But initial attempts to do this were unsuccessful. We'll go over kind of some of the problems that we had in a little bit. And so different solver settings were tested to determine what the appropriate setup would be to accurately simulate the shock location within the diverging section. Or yeah. Um, and we would consider success by matching the simulation results to within a 5% difference of an analytical solution that I'll go over in a second. And this would validate Fluent as a compressible flow solver specifically for a shockwave location in a converging diverging nozzle. So going into the analytical solution, like I mentioned, we took an example problem from Hibbeler's fluid mechanics and used the geometry and some of the pressure information that we got from that problem. And we determined what outlet pressure would be necessary to cause a shock wave in the diverging section. Then we solved for 4 values to use as metrics to match with our simulation results and see how our accuracy was comparing. And those are shown here. So shock location is a uh, axial location from the inlet, so that's 0.392 meters from the inlet. And then the shock area is the cross-sectional area at that location. And then the maximum Mach number occurs immediately prior to the shock wave, and then outlet Mach number, of course, occurs at the outlet. So this is our baseline case in Fluent that we used. We based all of our following simulations on it. We used a steady state inviscid density-based solver, and we used air as our material. We treated it as an ideal gas, so that was how we used to solve for the properties. Specific heat of 1010 joules per kilogram Kelvin. And then we used an implicit formulation, a rho FDS flux type, a least squares cell-based gradient, a second order upline flow, and a Carnot number of 5. Now, this is a steady state simulation, but Fluent uses explicit time marching even for steady state simulations, which is why we have a Carnot number defined. And then we ran each simulation for 100,000 iterations and took the values at the 100,000th iteration. So this is our baseline mesh that we used based on the geometry from that example problem. So we've got it's a 2-dimensional simplification of a 3-dimensional phenomenon. It's axisymmetric around an axis of symmetry that I'll show in a second. And it is the first refinement of its kind for this mesh in particular. So yeah, inlet on the left, outlet on the right, throat in the middle. And then, like I said, axis symmetry is that yellow line that you see there. So like I mentioned, we're going to talk about some of the previous work that we did. We'll go through this pretty quick, but this is an example of a 3-dimensional mesh, and it's a quarter type, which means it's a quarter of the cross-sectional area, as opposed to an axisymmetric. And then this is the third refinement of its kind, and again, same kind of locations within the nozzle. This is a 1-dimensional simplification, and again, also axisymmetric, and it is the second refinement of its kind. Just examples of some of the meshes that were tested. Yeah, same geometric parameters. So this is an interesting effect that we were having trouble with testing these different meshes. Was we were noticing that the different meshes affected the shock shape. So here you can kind of see the meshes outlined over this contour plot. You got your shock positioned here, and a lot of the shocks, as this one is not, were not normal to the nozzle center line, which is how the behavior would typically act. And in this case, you can see that the shock kind of follows the angle of the mesh elements. And this would suggest that angle of the mesh elements have something to do with the shock curvature. And then we'll just look at some examples of the changing shock shape with uh, different meshes. So these are all going to be three-dimensional quarter type and different refinements. So you can see here, we've got compared to analytical shock location. And if we change it, um, pretty similar, but there's some differences, especially in the way that the Mach number behaves after the fact of the shock wave. And then here you can see it's very different. If we zoom in, we have a discontinuity in our shock wave, which is obviously not supposed to happen. And we have inconsistent properties downstream of the shock wave. So we've got pretty consistent here, but then very different up at the top. And then if we look, oh, this just gives a better example. You can kind of see it's indented um, at the top right there. And it's not entirely normal, which is an issue. And then we also, if we look at their Mach number is supposed to be 1 at the throat, we were having some issues with the shape there as well. And then this is the final refinement of that mesh. And it's a little better. It's straighter and doesn't have a distinct discontinuity, but it has much less consistency after the fact of the shock wave, which is a serious problem. So moving on to the solver settings that we tested, this is with the original mesh we showed, that green mesh that we showed you. We used a prevent reverse flow command. It's something you can define in the inlet and the outlet. We defined or reduced the Courant number to 0.5. We tested an explicit formulation with Courant numbers of 1 and 0.1, and also 1 and 2 residual smoothing iterations. We used a target mass flow rate, a Green-Gauss cell-based discretization scheme, a AUSM flux type, um, a number of other residual smoothing iterations, and then as well as a transient formulation simulation. Combinations, that's just, we tested all of these other models were like changing one parameter and seeing what would happen. And then combinations was taking the most successful ones and putting them together and seeing, oh, can we make them be accurate together? And then we also refined the mesh at the shock area to see if that would increase our accuracy. So getting into our results, this is an example of a Mach number contour that we got using that mesh that we showed you. This is with explicit formulation and 2 residual smoothing iterations. So you can see that radial or axial shock location from the inlet is 0.359 meters. And that this is the most accurate shock location that we were able to achieve. And if you remember, the original shock location of the analytical solution was 0.392, so 8.8% difference is what we calculated. This is the radius of the shock that we used to calculate the area that we mentioned. And then we got our maximum Mach number, 2.13, occurring immediately prior to the shock, and then our outlet Mach number at the outlet. So for the most accurate performers for the data that we found, these were taken again at the 100,000th iteration. You can see for shock location and shock area, those are geometrically dependent, so they both occurred with that model with 2 residual smoothing iterations we just showed you. We achieved 8.8% difference and 17.1% difference, which were not within the 5 that we were looking for. And then for the maximum Mach number, the outlet Mach number, we did achieve within the 5% difference, but they were with different simulations, 5 residual smoothings and 4. And again, these are all single point values. So seemingly the best performers all contain residual smoothing, which is interesting, and it would imply that they improve the accuracy of our models. However, residual smoothing is related to convergence speed and thus should not affect your final solution. And in addition, increasing the number of residual smoothing iterations doesn't increase your accuracy, which we'll show you in just a second. So you can see here, basically we increased the number of residual smoothing iterations all the way up to 27, and then measure the shock location at the 100,000th iteration to see what kind of variance we would get. And the two residual smoothing iteration model that we showed you that contour plot of still remain the most accurate, even though all of these models were tested. And you'll notice here that the shock location is varying a lot between 0.34 meters and 0.36 meters. And these are different models, but they shouldn't change because all we're changing is the residual smoothing. So we decided to investigate what kind of variation would we achieve in a single model. And we'd measure the shock location at 5 distinct points, and then also compute the maximum and outlet Mach number for each iteration. So this is the, excuse me, variation of the shock location at those 5 distinct points that we measured. And this is taken from a model with 4 residual smoothings. And so you can see it's hovering between, or fluctuating between 11 and 14% error from the analytical. And there's a similar effect for shock area because, again, they're geometrically dependent. So from this, we can see that shock information at 100,000 iterations, that single point, does not represent all the model results. And we can see that numerical uncertainty arises from taking a single value at the simulation conclusion, and we really need to be taking the average over all the iterations instead of that single point. So if we look at the Mach number, much more variation seen here. This is again from that 4 residual smoothing iteration model. The outlet Mach number is in blue, varying all the way up to 40, and then the maximum Mach number is in orange, 0 to 15% from the analytical, and like I said, outlet is 0 to 40. So again, numerical uncertainty arising from taking the Mach number results at a single point and not over an average. And this fluctuation, even if we were to take the average, is still very excessive, especially for the Mach number. So these are all of the models that we tested. They're the 4 parameters that we mentioned that we calculated and we used for comparison. And this was a total of 33 models using that original mesh that we showed you. And they have their percent differences modeled. So in summary, despite the numerical uncertainty that we discussed, 5% difference was achieved for Mach number values, but not for the shock results. And again, these were single point values and not averages. And so fluctuation that we saw, it demonstrated a lot of numerical uncertainty. And this can be kind of illustrated in, we stopped the model at 100,000 iterations. If we stopped it at 105,000, it would probably yield a significantly different result, which is a problem. So ideally, we'd be able to reduce this variation. And so further study, we would reevaluate the previous models that we tested, those 33 that we showed, and we would look at the averages and the fluctuation occurring in each individual model. We only tested that one model and saw the fluctuation throughout all the iterations. We would also add undue relaxation to reduce the variation to try and mitigate that. And then we would also consider that this is an unsteady phenomenon. We assumed in our model that it was a steady state simulation, and the analytical solution also assumes that it's one-dimensional and steady state. In reality, this is truly an unsteady phenomenon, and the model does want to match this behavior. Yeah, thank you guys for listening. This QR code will take you to some of Dr. Strasser's work from the other students that I work with. And yeah, if you're interested, check it out. Thank you guys. Time. We have a couple of minutes for questions. Go ahead. So you mentioned about numerical uncertainty, 5%. So is that discrepancy or some numerical uncertainty analysis for CFD ports were carried out? I'm sorry, I don't know if I understand what you're asking. No, there is something called numerical uncertainty analysis in CFD ports. Okay. So was that carried out in this CFD validation? So we took, originally we assumed that we could take an accurate answer from a single point at the 100,000th iteration, and then we realized that it was fluctuating a lot, and we didn't, and we started realizing that we needed to evaluate how that would affect our answer and what kind of like error bars we would need to have on the answer. And so I think, no, we did not take that into account till the end. And that was kind of what the conclusion was, we need to do that instead. Yeah.
Yes. What is the diameter, the inlet diameter and the outlet diameter? Did you show that, or is it?
I did not show that. It was, I believe, the radius is 0.25, and so it'd be a 0.5 meter diameter.
Did you think about this geometry because people use this geometry, or is just random?
So this project was to just validate Fluent as being able to accurately simulate the location. And so we took an example problem from a textbook and just used that geometry. And so if we were able to accurately simulate it, then you'd be like, okay, we can trust this model, and we can say, okay, change the diameter, and then we'll accurately simulate it.
Just think about, like, you want to test it, right?
Yeah.
I don't know. It's
Yeah.
it would be a lot of.
Yeah.
But it's a nice geometry.
Yeah.
Now you used your analytic solution in 1D, right?
Yes.
And its metal characteristics.
Metal characteristics.
No. How did they get the analytic method of characteristics or something different?
Um,
It's just using the normal shock tables. Normal shock tables.
oh, yes.
Yeah. But I'm just thinking that the actual flow here would be at least 2D.
Yeah, so that's why we tried about 30 different meshes, trying to make it actually 2D.
Yeah.
But we're so far off the analytical solution, there's no way that's the 2D, 1D difference, because we were able to make the shock 1D vertical, perfectly 1D. And that's why we ran an inviscid solver. We wanted it 1D. We had no shear, distribution.
Yeah, but I'm saying how, if somebody could get a 2D analytic solution, which you can't, would it give you results which are further out or closer out?
Yeah.
There's no way of getting a 1D solution theoretical with a flow which is 2D, right?
Yeah.
Or is it perhaps 3D actually?
Yeah. I mean, because it was at least numerically.
So I'm saying, how close do we want to get to the 1D solution for a 2D problem? I don't know.
Yeah.
But the method of characteristics would be a good try for that. Thank you. That's good.
Okay. All right. Good. Thank you very much.
Thank you.